All right, this is the second part of semantic validity for modal logic for the system K. We'll talk about a few different things in this video. The first one will be how to diagram worlds. So let's say we have this scenario right here. You have world 1 where not P is true and not Q is true. Notice it doesn't access itself, but it does access W2 and W3, world 2 and world 3. At world 2, P and Q are true. At world 3, P is true, but not Q is not true. And notice world 3 is the only one that accesses itself. Alright, well there's a way of diagramming this out, and here's the way it would be. First, the set of worlds that we have available here, the set of worlds, and that's a capital W, equals, and here is the set sign, equals world 1, world 2, and world 3. Those are your three worlds that you have. And then you have these relations. Here's what R does. R relates world 1 to world 2. It relates world 1 to world 3. And it relates world 3 to world 3. So here's 1 to 2, here's 1 to 3, and here's 3 to 3. But you don't usually have to write this, and R relates no other worlds. So we've captured all the relations. And in world 1, so the truth value at world 1 of P right here is 0. The truth value at world 1 of Q is also 0 because you have the knots. Remember, this should be familiar from propositional calculus. All we're doing differently is adding the worlds that we're talking about at the bottom of the V sub world 1, right? At world 2, P is true and Q is true, right? There's no knots, so P equals 1 and Q equals 1. At world 3, P is true and Q is false, so P equals 1 and Q equals 0. And then you can draw this out, and it doesn't have to look exactly like this, but I mean in this formation here. Excuse me. It doesn't have to look like this same formation, but it should look something like this, where world 1 has arrows to world 2 and world 3. Close to world 1 you have the not P and the not Q, whatever's true and false there, and close to world 2 you have the P and the Q. 3 has this little, this guy that tells you that 3 accesses itself, and P and not Q is at world 3. So if you have a setup like this, here's what you would write about it. Here's how you would make a model of that world, in other words. And when we do counter models, that becomes important. All right. Now let's take that same thing, right, where we have this right here is what I have right here, and this up here is what I have right here, and I just erased all the circles so we can add more things in here. You could also see, and you don't usually write these, but you can also see what else is true here. So if P and Q are true at W2, then you know that P and Q is true at W2, right? Remember we talked about possibly Q is only true if at W2 if there's some world where W2 relates to where Q is true, but W2 doesn't relate to any worlds, so it's not true that possibly Q at W2. World 1 relates to W2 and W3. At world 1 we know not P and not Q are true, but P and Q is true here, and W1 is related to W2, so possibly P and Q is true here. This one I'll talk about in just a second. Let's look at W3. At W3, P and not Q are true, right? We saw here. At W3, and W3 accesses only itself. So all the worlds in W3 accesses P is true, because the only one that accesses itself, and P is true at itself. So necessarily P is true. Now since necessarily P is true down here, and W1 accesses that, there is some world that W1 accesses where necessarily P is true, so possibly necessarily Q, that should be, sorry, necessarily P is true. Let's change that. Possibly necessarily P is true. And that's, again, because necessarily P is true at W3, W1 accesses that world, so possibly necessarily P is true at W1, and that's because of those true conditions, right? Possibly A is true if there's some world that W accesses where A is true. So possibly necessarily P is true if there's some world where W1 accesses where necessarily P is true. All right, so this is how you diagram worlds, and here's some extra stuff that you could do with that. The next thing we're going to talk about is two different relations. One is that the truth value of not possibly A is equal to the truth value of necessarily not A. Now that just makes intuitive sense off the bat. If you're going to say it's not the case that something is possible, then it's necessarily the case that that's not that thing, right? So if it's not possible that cats are nice, then necessarily cats are not nice. That's sort of what this would mean. But you can prove it logically, and here's how you would do it. First, the truth value at W of not possibly A is 1, if and only if the truth value at W of possibly A is 0. And that's from this rule right here, right? So, I mean, not this is true if same thing, this is false. And then, let me erase this, and then possibly A, this thing right here, is false if and only if for all worlds that W relates to, A is false. And that's the truth, that's the rule for this down here, right? So remember, this rule is if there is some world that W accesses where A is true, then possibly A is true. And if there's not any world that W accesses where A is true, then possibly A is false. Alright, let me erase my guys again. For all W, so here we have this right here is equal to this right here, right? For all W prime such that W is related to W prime, the truth value at W prime of A is 0 if and only if for all W prime such as W is related to W prime, the truth value at W prime is not A is 1 is true. And that's this right here, right? So in other words, here's what you got going on in this kind of thing. You have a world W and a world W1, or W prime, sorry, W prime, and for all of these W primes that W is related to, A is false, and if A is false at all these worlds, then not A is true. Alright, erase all these inks. So for all W prime such that WR is related to W prime, the truth value W prime of not A equals 1, that's this right here, if and only if the truth value at W of necessarily not A equals 1. And that is this right here. So again, let's say we have W and W prime, and we said the truth value of A is 0 at W prime, so the truth value of not A is 1 at W prime. W prime, let's pretend W prime is the only world that W is related to, but this truth, what it's saying is, you know, for all these W primes, not A is true, right? And that's the case if and only if necessarily not A. So from all these, for all the worlds that W accesses, not A is true, then necessarily not A is true. So notice how this proof goes down. It's like transitive property, right? So possibly not A is 1 if this, if and only if this, if and only if, and if and only if that, if and only if this, and if and only if that, if and only if this, right? So at the end of the day, you get this if and only if that, and that's what this says right here. So truth value at W of not possibly A is 1 if and only if the truth value at W of necessarily not A is 1. Very similar proof for this one. The truth value W of not necessarily A equals the truth value of possibly not A. And that again makes intuitive sense, because you're saying it's not the case that A has to be true if it's possibly the case that A is false. Something like that. And we're going to do the same kind of proof, right? We'll start off with this guy. That's what this is right here. The truth value of at a world of not necessarily A is 1, if and only if the truth value of that same thing I'm not sorry, not the same thing, but of necessarily A is 0. And that's this rule right here, right? That's the not rule. So the truth value of not this is 1 if the truth value of that same thing is 0. And then, well, you know, again, this goes down here. So the truth value of necessarily A equals 0 if and only if there's some world that W, this thing, is related to such that A equals 0 at that world. And that is this rule down here, right? Let me erase this so it's not as confusing. So again, this is basically this right here. So this is true. There's some world that W is related to such that A equals 0 if and only if for that world not A is true. Not A is true. So A is false at that world if not A is true at that world. So again, if we look at this, we say W, let's say all the worlds that W accesses are W prime, and at W prime A is false. That means not A is true at W prime. That's what this is saying. And again, we'll take this and move it down here and say not A is true at all W primes, at some W prime that, some W prime is what we're worried about. So W could relate to some other worlds where A is true. We're talking about necessarily A, that's what we're worried about. So for some W prime such that W is related to not A is true if and only if it's the case that possibly not A is true, right? So, and that is this rule right here. So since from here not A is true, then this rule is satisfied, so possibly not A is true from this world. Now you put all those together, you start here at not necessarily A is true, and you end up if and only if possibly not A is true. And that is this right here. So what those two proofs show are that you can always switch between these two, right? If you ever have a not necessarily A, you can swap it with possibly not A. All right, finally, what does validity mean for, semantic validity mean for modal logic? It means it's truth preserving at all worlds of all interpretations. All right, so here we have, this is semantic validity, remember the sideways T with the two prongs. And this Greek sigma means the set of, these are the premises, right? The set of formulae that are the premises, whatever it is that you use to prove the conclusion. Remember, it might be empty, it might have some premises in it, who knows? These premises semantically entail the conclusion A, if and only if, for all interpretations, all ways of giving the true and false values, excuse me, and all worlds that are members of this W, if the truth value at all those worlds for all the formulae that are in sigma, so all the formulae that are in the premises equals 1, then the truth value of at all those worlds of A equals 1. All right, and the A is the conclusion. So the reason they have this extra stuff here is what they're saying is inside of this sigma, all of the formulae that are inside, all the premises that you use, if they're all true, then the conclusion has to be true. Basically, it's the same thing that we did for propositional calculus, where all the premises are true for this, no matter how you shake out all the truth values. Whenever all the premises are true for sigma, the conclusion has to be true. And if that's the case, you have semantic validity. And well, let's not worry about this right now. So that means something like, if you have let's say necessarily A is true, and at let's say at W, right? We want to say necessarily A is true at W, and we want to say not A at W entails A at W, and let's say W relates to itself, right? Then this whole thing it follows if there's no way that I can assign truth values to A where this becomes true and this becomes false. Let's say W only relates to itself. So if I give A a 1, if I say A is true, and that as in this world it relates to itself, that would mean necessarily A is true. So necessarily A is true, but I said A was true, so it necessarily A is true and A is true. Sweet, that means that we're good. Let's say I say A is false. So there is a world that W relates to where A is false, so necessarily A is false, but I don't have to worry about that because the conclusion is also false. A is false. So this would be semantic entailment right here. All right, and that's the end of this video. You can also see here, by the way, why they call these boxes and diamonds. They call them they're non-truth functional. So they're not worried about you can't set them up, and you can't go like, you know, if A is 1 and A is 0, right, and then say, well, what does necessarily A mean? Because you have to worry about all these relations. So you can't just do those truth tables that we talked about before. But that's the end of the video, and if you have any questions, we'll answer them tomorrow.